So last time we talked about the spring mass system, which is it's another way of saying the harmonic oscillator. So I wanted to look now at a higher dimensional version of the harmonic oscillator, just because I think it's useful, sets a stage for the types of things that can happen in higher dimensional Hamiltonian systems. So let's look at a 2 degree of freedom example. Very simple. It's just the double harmonic oscillator. So we start with, we could just directly write down, that's what we got to last time. For particles, you could directly write down kinetic and potential energy. The kinetic energy, and I'm just going to assume unit mass, so I'm not even going to write m. If we say the kinetic energy, it's 1/2, and I'll write it this way. Kinetic energy of, you could think of it as, we've got 2 components, we've got 2 particles, and the potential energy will just be a quadratic omega-1 q1 squared plus omega-2 q2 squared. If you want to have something visual in mind, you might think of a rigid frame. I don't think I have one of these in my lab, but if we had a rigid frame with a mass connected by springs to both sides, and maybe these springs have a different stiffness, and that's why we get a different omega-1 and omega-2. If I were to displace this mass, then the springs will be at a different location, and this thing will oscillate, right? If I let go, it's going to want to oscillate around its equilibrium position, but in some interesting way. So what is that? So we have a Hamiltonian that we would write it as a function of Q's and P's. So Q1, Q2, P1, P2. And it's just this T plus V. We could pretty easily write down what Hamilton's equations are. And I will leave it as an exercise, but I'll just tell you what it is, right? Q1 dot is going to be partial H, partial P1, which just gives us P1. And we can group these however we want. I'll do P1 dot. P1 dot is negative partial H, partial Q1. So that gives us negative omega-1 Q1. And then same thing for Q2 dot is P2, and P2 dot is negative omega-2 Q2. So these are completely uncoupled. The 2 oscillators are not coupled. You've got the dynamics in the Q1 P1 plane, and then the dynamics in the Q2 P2 plane. Let me just write that. They're uncoupled in that, right? They don't affect each other. And these are simple enough. It looks a lot like the spring mass system from last time. So we sort of know what the dynamics will look like in Q1, P1, right? If you start with some initial condition, this is just going to oscillate around. And we'll actually have the oscillations have frequency make 1. And similarly, Q2, P2. Let's say we start with some other initial condition. It doesn't matter what the amplitude is, we'll have the same frequency. That's one of the key things about a harmonic oscillator. It makes it different from other things that have nonlinear terms, right? These ODEs are purely linear, so they're simple to solve. So here the frequency is omega 2. And the terminology, I don't know if I've mentioned this terminology. We refer to the Q1, the QI PI plane is called the ith canonical plane. Maybe I'll put a little terminology note. So the QI PI plane. So there's this special grouping of variables, right? Q1 is going to be intimately related to P1 because P1 is its conjugate momentum. Q1 is only going to be somehow distantly related to P2. It's sometimes called the canonical plane or symplectic plane. Different books have different terminology. Again, this word symplectic, if I remember my etymology correctly, has something to do with complex numbers. Now, another way that we could look at this is if we were to look in the full 4-dimensional phase space, right? We've got Q1, Q2, P1, P2. Now, I can't easily draw 4 dimensions, but I could try. Right, here's Q1, Q2, P1, P2. And then think of it as we're just looking at, here is a 2D projection onto the Q1, P1 plane. And then we could look at, so the dynamics here, maybe I'll draw it in green or something, right? There's some trajectory. What is it doing? But if you project onto the canonical planes, it's all very well understood. It's just things are just moving on circles, unless you're at the origin and then there's no motion. If you think of these as kind of modes of this system up here with the mass and the springs, there's going to be a mode, maybe this direction is like the number 1 direction and this direction is the number 2 direction. You've got 2 modes of motion, and for small enough displacements, they are not coupled. So we would say maybe this is the motion in mode 1 up here, and then this is the motion in mode 2. But what do things look like in the 4-dimensional phase space? It turns out they look like, it looks like motion on a torus. So for a general initial condition in the 4D phase space, there is a 2-dimensional torus of the surface of a donut. And the way to understand that would be if we were to sort of track where we are in each cycle and use an angle. So let's say if I call this angle phi1, and same thing here. I just sort of will measure the angle from the Q2 axis, and here's phi2. Well, these angles are just sort of circulating around. This is the phase of the oscillation in each mode. So QI is the phase of the oscillation in mode I. And you could think of it as just, it's the angle tracking where we are in these periodic loops in each of the canonical planes. But you could also think of them as, this is the angular variable of a polar coordinate, right? And there'd be some other variable related to the amplitude. I don't know, maybe call this A1, the amplitude A2. This might be too tiny to see, but anyway. This will become clear later, but instead of amplitudes, we have things related to amplitudes. So we parameterize the amplitude with an action variable. I think in the first lecture, I mentioned something about action angle variables being sort of this second best way of describing a system. A lot better than just the original given coordinates. So instead of amplitudes A1 and A2, we have action variables. And so in this case, we have two. So these are actions. Phi1 and Phi2 are the angles. So instead of phase, we say angles. So instead of writing things in terms of these original variables, Q1, Q2, P1, P2, we could write them in terms of angles and actions. Right, the angle coordinates, they're still phase-space coordinates, and they're kind of like polar coordinates, but not exactly. And these angles, you know, and here's the key thing: the angles are like our new coordinates; they're like the new Q's, and the corresponding momenta are not the amplitudes of the phase; they're these other things called the actions. So these are the momenta or actions. They're called actions when they are momenta corresponding to angles. And what we have is that we could think of angular variables. Ooh, maybe I'll use the colors because colors are fun. Here's the Phi1 angle, and then the other one, I think I used blue. That's 2. So motion is happening, right? The amplitudes don't change. It's just the angles that change, and they just sort of go around with the constant frequency, constant rate, omega 1 and omega 2, respectively. So what we have in the 4-dimensional phase space we have motion on a torus. So where one of the directions corresponds to Phi1, the other direction corresponds to Phi2, and some general initial condition is going to be winding along these things. It won't be as sort of jagged and crazy as this, but hopefully you get the idea. Just by the very fact that we can cast things in terms of two angles, we have motion on a torus. The size of the torus is given by these two action parameters. So we would say that the phase portrait, so in this original space up here, right, where we didn't really have any understanding of what's going on, the motion is really just a two-parameter family of two tori. So the four-dimensional phase space, it's just a whole bunch of nested tori. Try to get your mind around that. We would think of nested tori in 3D, and you could just think of like one donut inside another donut going on forever. But now think of donuts filling four-dimensional space. So the 4D phase space, we technically say it's a two-parameter family of two tori. In fact, this was a double harmonic oscillator. If we had a triple harmonic oscillator, so 3 Qs and 3 Ps, if they're all uncoupled, then the 6-dimensional phase space would be a 3-parameter family of 3 tori. You can see where this is going. If we have an n degree of freedom system of harmonic oscillators, we have n parameter family of n tori. And we'll say more about that later. What it means about the motion, it means the motion in general will be quasiperiodic. Motion is quasiperiodic. So if you took my nonlinear dynamics class and I discussed motion on a torus, the motion on a torus is generally quasiperiodic, meaning there's not one period, there's in general two. So if we were to do this might be familiar, if you were to do like a Fourier transform of the motion, you would have two peaks, one at omega 1 and one at omega 2. So a spectrogram means in the signal, if you were to look at what Q1 and Q2 do, right, they'll be kind of pure motion, but this doesn't just hold for the double harmonic oscillator. If you have any system where if you kind of follow some representative Q as a function of time, and it seems to be, I don't know how to make a signal with two periods. So here, this kind of looks like there's a long frequency and a short frequency sort of superimposed on top. And that is, in some sense, a very generic thing you'll see in Hamiltonian systems. Now that's if we had two uncoupled harmonic oscillators. It's probably worth looking at the pendulum because the pendulum for very small, here's a pendulum. I got my magic pencil swinging back and forth. All right, magic pencil swinging back and forth with no damping would be a pure pendulum. And for low angles, it looks like a harmonic oscillator, but when you go to larger and larger amplitudes, then it's not a harmonic oscillator. And I'm always going to like try to rescale things so we don't have any unnecessary cluttering parameters. So if we appropriately rescale, this is time and the length, then we would get, right, the Hamiltonian is T plus V. We're talking about the pendulum. Here's a pendulum. Maybe I won't, yeah, I want it to be able to swing all the way around. So here's a pivot point, and then here's the mass. And we'll be tracking the angle, but I'll call the angle Q. So this is a planar pendulum. It's 1 degree of freedom. Kinetic energy, 1/2 p squared. I won't even put subscripts because there's just 1 degree of freedom. The potential energy due to gravity is going down, but we've rescaled everything, so there's not, G is not going to show up because we've rescaled time and length to just kind of make it unit acceleration. So this will be, the potential energy is negative cosine Q. Right, we do non-dimensionalization just to sort of get at the essence of how do things depend on phase-space parameters, phase-space variables, not parameters like mass or G or whatever. So the Hamiltonian is 1/2 p squared minus cosine Q. And right, we could write the Hamilton's equations. So Q dot is partial H partial P, which gives us P. It's easy. P dot is negative partial H partial Q. I always get confused with derivatives of sines and cosines. This works out to be negative sine Q. Okay. We could simulate that, or the trick we learned last time is that you could just look at isocontours of H. Right, this is just a function. H can interpret H as a height function. And we could look at isocontours, right, level sets of H. And that will reveal the phase portrait. It won't give us the direction of the arrows, but it'll give us plenty of information. So here's Q. Here's P. And so Q, we would say that Q is on the circle, but you could think of it as Q goes from negative pi to pi, and negative pi and pi are the same physical position, the vertical position. So I'll put that up here. This is negative pi, and over here, pi. For low values of H, I think for the minimum value of H, you just get a fixed point that's at the origin, and that would be the downward position of the pendulum, no motion, nothing terribly exciting. For slightly larger values, the isocontour will look like that. And you need to know that, well, P equals Q dot. So the motion has to be, when we're in the upper half plane, that means P equals Q dot is positive. So the motion is to the right. Q is increasing. And when P is negative, that means Q dot is negative. So Q is decreasing, so motion to the left. So that's how you know how to draw the arrows. For a slightly larger value of the isocontour, okay, we get this. And you usually only need like one arrow. Now this is not going to follow the pattern up above where all the amplitudes, for each amplitude, the frequency is the same. You can kind of imagine limiting cases where you're really close to inverted. It takes a long time to get back up. And if we get larger and larger, we get this thing kind of distorting. This is kind of looking like a after you've taken a red-eye flight. The limiting case would be if you start at there's an equilibrium, it's an unstable equilibrium, the inverted pendulum position, right? And if you just slightly nudge away from the inverted pendulum position, I'll look at the negative pi, it'll sort of go off. And there's a special trajectory which starts, it asymptotically leaves the inverted position and then asymptotically approaches from the other side. And there's two of those. There's going the clockwise way and the counterclockwise way. And this would be sort of a critical value of the energy, because above that, we've got other trajectories. And these are trajectories which are called circulating trajectories. So we're plotting, I'm basically just plotting isocontours of h, but only between negative pi and pi, and then knowing my rule for how to put the arrows. So red is low energy. And by energy, I mean Hamiltonian energy, right? This has units of total energy. Blue is a critical value of energy. Maybe it's a critical intermediate energy. And then green is high energy. And these high energy things, it's where you hit the pendulum so hard, it's just sort of circulating around. And it slows down as it gets near the top. And that slowing down as it gets near the top is, right, this distance is lowest near the top, and then it goes high, and then it goes low again. Just sort of showing that in yellow, right? That's because P equals Q dot. So we have highest speeds near the bottom, and then low speeds near the top, and high speeds and low speeds. So that's, you could just get that from the isocontours. Sometimes to remind myself that these two are physically the same, I'll do this weird thing that just says we identify these two sides. Right, since Q equals minus pi and Q equals plus pi are physically the same location. We could take that even further. And if you imagine taking the screen, printing it out, and then cutting along those dashed lines at plus or minus pi and folding it over, you get a cylinder. So really, since Q is a circular variable, or angular variable, the phase space is the cylinder, or it's cylindrical, right? So this is actually what I called Q, and this is what I call P. All right, that's the, it has implications if you know the topology of your phase space cylinder. Like the cylinder has a certain type of topology, right? You go in one direction, you come back. So topology of phase space is significant. Why is that? It puts constraints, kind of built-in constraints. It puts constraints on the type of motion that can happen, or the type of dynamics. Often in engineering classes, when people will plot angles, they'll just sort of plot angles and make them go up and up and up. When really, if this physically represents the same thing, you shouldn't have it go up and up and up. You should always make it go between plus or minus pi. That's one of my pet peeves. All right, so and why is it significant in putting constraints on the types of dynamics? Again, there's this from the nonlinear dynamics, we talked about index theory. So there's this theory that says, depending on the type of what the topology of your space is, only certain types of dynamics are possible or impossible. So if your dynamics happens on a sphere, then there have to be points where there have to be equilibrium points. Whereas if it's the flat real plane, there don't have to be equilibrium points. I think the cylinder in general does not have to have fixed points, but torus also doesn't have to have fixed points, but if it does, they have to come in certain pairs. That's another thing. But if you want, yeah, if you want to know more, look up index theory, particular Poincaré index theory. Poincaré's done a lot of stuff. This is the X notation from last time where I talked about the Q matrix. So I kind of informally call it the X notation, but other people call it the symplectic notation. Just because I use the symbol X. And the nice thing about it is it emphasizes the equality of the Q's and P's. Maybe I'll put that in quotes, the equal status of the Q's and P's. Very different from the Lagrangian formalism. In the Lagrangian formalism, they're the configuration variables, the Q's, and then the Q dots are definitely related to those as the time rates of change. And you might be thinking, well, all we've done already is just the P's are just the Q dots maybe multiplied by a mass or something. What's the big deal? It'll be a big deal eventually. Maybe it's not a big deal yet, but we combine these into one vector, a column vector. So Q is the column vector of the Q's, P is the column vector of the P's. So Q1 all the way down to Qn, and P1 all the way down to Pn. It's important they be grouped this way, and different authors will group them in different ways. But I do the Q's and then the P's. Some people do Q1, P1, Q2, P2, all the way down, but you don't want to do that. And so I said this is these are components of X vector that's 2n dimensional. So we could also say this goes from Q1 to Qn, Qn plus 1 all the way down to Q2n. Right? We're thinking of an n degree of freedom system. If it's n degrees of freedom, that means it's 2n phase space variables. So this X is a 2n dimensional vector. Another way to think of that is it's an element of R2n. And then instead of saying that the Hamiltonian is a function of Q and P, we just say, no. This is just Hamiltonian is a function of X. And then we write the gradient of H with respect to the X variables. So yeah, this thing appears in equality. So this is the gradient with respect to the X variables. Another way that sometimes gets written is DH, but that might be confusing. Gradient of H. So gradient of H, we know how to write the gradient, right? H is a scalar function. So its gradient is going to be a 2n dimensional vector with components that look like partial H, partial x1, all the way down to partial H, partial x2n. And in terms of the original Q's and P's, this is partial H, partial Q1, all the way down to partial H, partial Pn. Now, why do we want to do this? It's because it allows us to write Hamilton's equations in a really compact and nice way. We first define this matrix J. And now we're thinking of the n degree of freedom case. So this will be, it's mostly zeros and then a few ones. So I've written it in this block diagonal form. 0 means the n by n matrix of zeros. Maybe I'll even do that. 0n is n by n matrix of zeros. This capital 1 sub n is the n by n identity matrix. This thing is called the canonical symplectic matrix, or sometimes people just call it the canonical matrix, or sometimes just the symplectic matrix. And it has the same properties that we talked about last time. It has that weird property that makes it look like a matrix version of the complex numbers, right? Because j squared equals negative the 2n by 2n identity matrix. Ooh. Now, Hamilton's equations can be written in a nice form. So they can be written very compactly as x dot equals j, right? This is a 2n by 2n matrix times the gradient of h. And the gradient of h is typically a function of h. So x dot is an n-dimensional vector, 2n-dimensional vector. J times gradient of h is a 2n-dimensional vector. So this is a really nice, compact way to write Hamilton's equations. Sometimes we use this notation up here of the D. You might see that a lot. So I might kind of switch JDH, and then I don't have to use any Greek symbols. So that's nice. So in general, when we speak of dynamical systems, continuous dynamical systems, we're thinking of x dot equals f of x. Here, we've got a special form for f, right? Here, f of x equals j times the gradient of h. And this, if you were to work out what this is in terms of the original Q's, it's exactly what we would hope for. It's the canonical symplectic matrix. I mean, the Hamilton's canonical equations. It's just written in a really nice way. It goes from 1 to n. And this will be useful to us later, but I'll introduce it now because I did mention it last time. All right. There's some interesting properties for Hamilton's canonical equations. I'm thinking, without non-conservative forces. Let's leave that there. Hamilton's canonical equations are divergence-free. So if you viewed it as a fluid, you could calculate the divergence. What is, I guess, in terms of the way that we've written things, what's divergence? D. So write things that way. So this is going to be some scalar. I'll write it just in terms of the Q's. So I think it's easiest that way. This is kind of the divergence of our ODEs. This is partial Q1 of Q1 dot all the way up to partial Qn dot plus, now the next group is the P's, partial P1 dot all the way up to partial Pn dot. And now if you substitute in right? Hamilton's equations. What will you get? So this becomes partial Q1, partial H, partial P1 plus partial Qn, partial H, Pn plus partial P1. This is negative partial H, partial Q1. And maybe you see where this is going. It's partial Pn minus partial H, partial Qn. The terms cancel out pairwise. So for each Q and its corresponding momentum, these terms are opposite of each other, right? So H, by the equality of mixed partial derivatives, these two will cancel. So they cancel. And all of them cancel out pairwise. So this and this will cancel. All terms cancel pairwise. So the divergence equals 0. What does that mean? Divergence equaling 0 means that in the 2n-dimensional phase space, 2n-dimensional blobs will be preserved under the equations of motion. So this is 2n-dimensional volume preservation. Oops. Just like in a fluid, if we had a 2-dimensional fluid, the divergence-free fluid means that area in the 2D fluid will be conserved. Incompressibility arises from the divergence-free 3D fluid flow. So because of that, right, think of a water balloon. You could take a water balloon, but it's incompressible. So you try squeezing it, you could change its shape, but you're not changing its volume. And the same thing holds in any number of dimensions. So if you have a divergence-free system of ODEs, or a velocity field, a vector field in 2n dimensions, then in the 2n dimensional phase space, we haven't yet said anything about lower dimensional things, but 2n dimensional blobs, so blobs of full volume, will be preserved. Blob, I should say blob volumes. Preserved under Hamilton's equations. And so that's an interesting property. It's not a property of any particular trajectory. It's in some sense a property of a collective of trajectories. So we have 2n dimensional volume preservation. This sometimes goes under the name of Liouville's theorem. I guess Liouville was the first to do this simple calculation up here. I don't know, but there it is. So if you see Liouville's, like, oh, this follows Liouville's theorem. Yeah, that's all it means. So of course, this is true in 2D fluid flows. And why am I doing 2D and not 3D full fluid flow? So 2D fluid flows can be written in a Hamiltonian form. So 2D fluid flows So for an ideal fluid, in 2D, the velocity field for the fluid can be written in terms of a stream function, which is really just the Hamiltonian. So if you've taken a fluid course, you've probably seen this, right? And this, it gets mentioned in section 4.5 of the Hamel book. That's the student's guide to Lagrangians and Hamiltonians. And ideal fluid, I'm not an expert in ideal fluid, but I think it means inviscid and incompressible. And a stream function is just a scalar function, usually written as psi. So if we have psi, we usually write it in terms of position variables x and y, and then x dot, so how x changes in time for a fluid element. We sometimes write that as u, right? This is partial psi, partial y. So it's a partial derivative of the stream function, y dot. So the y velocity, we often write it as v when we talk about fluids, but following Hamilton's canonical equations, this is going to be negative partial psi, partial x. So what are these? These are just Hamilton's canonical equations with the stream function playing the role of the Hamiltonian function. At least mathematically, it's the same. So if we had if I were to sort of sketch, if you look at weather maps, they'll often just show the stream function at a particular height in the atmosphere. So you'll be seeing, you're actually seeing contours of the stream function, which means it shows the direction particles will go. So completely analogous to everything we've talked about for Hamiltonian systems. So they'll show, you know, there's a and sometimes it'll even have saddle points, meaning points where the stream function hits something else. You'll have situations like that. Maybe this is a typical picture you might see if you look on a global weather map. Something like that. So this is just showing isocontours of the stream function. And this is really useful in 2D fluid mechanics to just show the stream function. But then now you know how to interpret this, right? If I'm looking at this point, I know that I have a vector field. And here's the u component, here's the v component. And it's just going to come from certain derivatives of that stream function. So the stream function, think of it as a height function, and we're just plotting isocontours. Of course, when you have a time varying system, this isn't just a function of x and y. So for unsteady flows, psi is a function of x, y, and time, which just means you have a kind of moving stream function, moving isocontours. So yeah, it could depend on time. And because it's Hamilton's canonical equations, then for free, we get that it's incompressible, right? The U velocity, so just using typical fluid notation, x dot, y dot, or if we write it in the components of scalar U and scalar V, we know what these are: partial psi, partial y, negative partial psi, partial x, and this being divergence free is just a consequence. We write it in the usual fluid notation that way: partial x dot, partial x, partial y dot, partial y, and it's going to be 0. Partial psi, partial y, minus partial y, partial psi, partial x equals 0. So divergence free, incompressible, right? Blobs, if I had an initial blob, I'm not sure what color to make the blob. Here's a blob. Well, it's going to have to maintain. And so this blob that I chose is just going to get sort of stretched out along that one contour. Other blobs elsewhere, maybe they'll just sort of get rotated around. And if I have a blob right on that central part, it'll just sort of rotate. Okay. And then these because it's fluids, isocontours of the stream function are called, streamlines. But really, it's just, so 2D ideal fluids are just a small subset of the space of all possible Hamiltonian systems. So that's kind of cool. And the situation, of course, is the same for a 1 degree of freedom Hamiltonian system. But we can do some interpretation, and I'll probably end here. So the situation is analogous for a 1 degree of freedom Hamiltonian system. So you could literally view 1 degree of freedom Hamiltonian systems as fluids. If I were to, I'm going to sneak up here and show the pendulum, right? If I start with some blob of initial conditions, that blob is going, it's as if I just sort of dropped some dye into a fluid, but the fluid looks like this. It looks kind of weird. And so what's going to happen to this? This is going to, move around, but still be like a fluid. So all the intuition we build up from fluids, these 2D fluids, like the surface of a river, you could apply to 1 degree of freedom Hamiltonian systems. Of course, there's this weirdness, like most rivers don't have the topology of a cylinder. I have a flow on a Mobius strip. Maybe I could find that movie. It's kind of cool. It's 2D. Just has one side though. Yeah, what was I going to say here? So the situation being analogous for 1 degree of freedom Hamiltonian systems, we interpret it differently. Right, Q dot, P dot is partial H, partial P minus partial H, partial Q. So this vector field is incompressible. Right? Incompressibility and divergence, these are properties of vector fields. right? If you've done anything with electromagnetism, you had to deal with vector fields. It had to do with the direction of the electric and magnetic fields, and they're just vector fields. Well, this is a vector field. At every point in Q and P, there's a vector, and its components are Q dot and P dot. So this vector field is incompressible. Although it's not often said that way for Hamiltonian systems, we say it's volume preserving, but because we're in 2D, we say, so also known as area preserving. So blobs of phase space will maintain area. And interestingly, we can kind of relate this to a classical version of the Heisenberg uncertainty principle. I forgot how to spell Heisenberg. You know, I think most people were introduced to the name Heisenberg not from physics, but from Breaking Bad. It's kind of a interesting commentary on the culture. Anyway, so in quantum mechanics, and I might have the details wrong, so don't get on my case. Delta X, delta P, it's greater than or equal to something order 1 times Planck's constant. It might be like Planck's constant over 2 or something. But this is a constant. This is the main thing. And so this measures like delta X, delta P, if we were to look in the phase space or something. Here is the width in X. I'll call it, that's lowercase x. And then here is the width in P. Right, in this region, I'll call it D. So in quantum mechanics, it means that you can never ever even deal with a block that has an area less than h bar. In classical mechanics, we can, like, we could do measurements down to, let's say we're trying to look at something in orbit, and we can measure its, you know, x location to within 1 millimeter, and delta p, we can get it to, you know, something very small. We get something very small, but not 0. So there is still going to be an area. If we follow these corners, right, follow each of these corners, even over a small amount of time, we could look at how does this rectangle deform? And the rectangle will deform somehow. Maybe I'll look at this one first. It kind of deforms, goes to here. This other one takes another path. So we're looking at the evolution of the system through time, and this goes to, oops, here. I'll look at how this thing evolves. It goes to, I'm trying to make it go like there. And then this other one, how does it evolve? Let me go under that one and go up to here, up here. And maybe if we looked at the rest of the boundaries, they would do something. We're not looking at very, very short times. We might be looking at long times. So this thing deforms, has to maintain area. I feel like I got pretty close there. And this is the, so this would be D at time 0. And then here is that same domain, but at a time t greater than 0. So we let this thing flow. Now, if you just look at the circumscribing box, the circumscribing box is actually going to be bigger. And maybe I'll call this delta capital X. And then delta capital P. Now the area of D at time 0 needs to equal the area of D at time t, but that circumscribing box may have gotten bigger. Probably did. So we could express that as delta X, delta P. So in some sense, their uncertainty in both directions is going to be greater and then or equal to delta X, delta P, the original area, the original circumscribing box. So in some sense, uncertainty grows. And that's kind of interesting. The only way it wouldn't is if D just sort of parallel transported. And then you've got the same rectangle. But in any kind of interesting system with dynamics, you're not going to have that. So there is something like an uncertainty principle going on. We could also, and maybe I'll end with this thing, is just looking at the pendulum. If we were to apply to the pendulum. And I'm going to take a pendulum with a really large amplitude so that I get some nonlinear effect going on. But I'm still just going to call this X and P. So if I had the pendulum, maybe I start with a box that is pretty small. So my delta X and my delta P, let's just say they're roughly equal, and this is small. So this is my original area. Maybe I'll call that just D naught or something. Okay. And this would correspond physically. It's kind of nice to think of what does this mean physically. This would be the pendulum has, there's sort of a center, but then we've got some uncertainty about that, both in position and momenta. So that's just one way of visualizing it. Okay, we don't exactly know. Now, where does this central part of the trajectory go? Well, it goes somewhere. And then here at some later time, maybe even at the same value of X, that rectangle has deformed. I don't know what it's become, but it has to maintain the same area. Maybe it's stretched out along here. And it seems like our uncertainty has grown, at least in, right, think of uncertainty in X and uncertainty in P. It's gotten bigger. So if we were to just try to represent this, we're at the same kind of X location, but the uncertainty has grown. And I'm not doing this completely to scale, but you're just trying to give the idea. The uncertainty has grown. As time goes on, this little piece, just like a little patch of dye, right? In your coffee, you put in cream and things just stretch out into filaments. That's the same thing that's going to happen in any general 1-degree freedom Hamiltonian system. So this will go somewhere and we'll have even more stretching. It's kind of hard to keep that area the same, but I think you get the idea, right? And so now this circumscribing box is even bigger. And we've got lots more uncertainty. And this just goes on and on, right? This is going to get more and more filamentary until we observe the system again. when we measure the system with our machine precision, then we'll get back to finding out where it is. But it could be, in some sense, anywhere in the yellow box. So there are some, being a mechanical system, and a Hamiltonian system puts constraints on how uncertainty evolves. That's kind of the main point here. And you wouldn't get it as nice if you just use sort of the original Lagrangian variables in general. You need to cast your system in the Hamiltonian formalism to really do this carefully. So this would be d at time 0, and then here's d at some other time. Right. Being a mechanical system represented in the Hamiltonian formalism puts, we might say, dynamical constraints on how the uncertainty evolves. And just to make this dramatic, right? If you wait long enough, then maybe at some point, the region of uncertainty is this. It could be anywhere in the phase. You've got this really tiny filament thing. So it could be anywhere, and maybe it's really important to you to know the phase. So you can't let that happen, right? This filament just sort of starts stretching out like crazy. All right, I think that's enough for today. It's a lot of stuff.